Hello and welcome to the Superposition Guys podcast. My name is Yuval, and my guest today is Nikolaj Zinner, co-founder of Kvantify. Kvantify focuses on leverages quantum computing for real-world applications, notably in optimization and computational drug discovery, through a unique algorithm, FastVQE, that efficiently calculates small molecules. Despite challenges in scaling and skepticism around variational algorithms, Nikolaj is optimistic about the field's potential. He describes a pragmatic approach to technology selection, anticipates a gradual advancement in quantum computing, potentially marked by breakthroughs in encryption or efficient problem-solving algorithms, and much more. We hope you enjoy this episode. Hello, Nikolaj, and thank you for joining me today.
Hello, Yuval. Thank you for having me.
So who are you and what do you do?
Yeah, so I'm a physicist by training. So my background is in nuclear physics, theoretical nuclear physics. I used to do calculations for how stellar processes develop in stars when I was a graduate student. But I slowly developed an affinity for other kinds of physics related to sort of fundamental questions about quantum systems. What kind of atomic systems will bind? These kinds of things. Basically solving equations. I have an affinity for mathematics as a background, so I kind of transitioned into more fundamental quantum physics, which back then, which is now it's almost 20 years ago, right? It sounds horrible when you say it like that, but it is 20 years ago, and I sort of started to think about what's cool systems that you could develop at that time. It was cold atomic gases that we were actually looking at. So when I was a postdoc, this was the focus area, and it was just theoretical ideas and so on. But it quickly became over the years back then became possible to see a way through this into technology. And I think what's amazing now, basically having worked on that many years ago, is to see how that's coming to together. Everything is coming together, and you can actually build different kinds of quantum technology. I'm very interested in quantum computing, by the way, and you see the different platforms now. Of course, some of the stuff I worked on back then is now very applied in Rydberg atomic based quantum computing. So that's super cool to see. So that's kind of my background. I'm a professor of physics at Aarhus University in Denmark, but I am also now part of a startup called Kvantify. We started about 2 years ago and have a focus on use cases for quantum computing. So basically figuring out how you can use those machines that people are now building and that are sort of becoming very much reality now. And how can you leverage those machines out in coming as an academic, I would say, out in the real world. And I don't think that you can live with just sort of, if you just say, I have a textbook knowledge of that question, and I go and I look in the classic textbooks and I see, I can do all these kinds of fancy algorithms that are in the textbooks. That's all good and well, and that's enough of an argument to build the technology. I completely agree with that. But I think that we're now at a stage where you need to get into, you need to get into industry, find the different sort of value chains out in industry and figure out how these quantum algorithms will actually integrate into workflows, into real workflows. So that's what we do in Kvantify.
What is the unique angle for the company? I mean, as you mentioned, many people are looking at these kind of problems. Are you able to extract more out of qubits than others? Do you have a unique algorithm? Are you combining classical and quantum? Is that the angle? What's unique about Kvantify?
I think we do similar stuff to other people. I'm going to come back to one thing that I want to mention where I think that we're basically very, very unique in the market. But, combining, just to your question about, are you combining classical, quantum in some, new ways and so on? I think that we are, but I would also say that I think that, we all are, and I think sometimes people forget the fact that, a compute process, even in the future, is probably going to be like 90% classical stuff, and then you port 10% to a quantum computer, where the quantum computer really matters, right? So our company, the way that we are based, and the philosophy of that is that you also need to take that into account when you start building your team. So when we started building Kvantify, and recruiting the first people and all this, we really said, look, we need competences really across a stack of different things, including classical algorithms, software developers, domain experts, and so on. And so we have domain experts in various fields, but mainly in optimization and in things related to computational drug discovery. So if you want to say, what's our play here, those are probably the two things where I would say that there's the most, promise, and that's where we sort of, spend most of our time. Now, coming back to in terms of your question about, where's, can I come up with an example of where I think that we're maybe mostly unique? It's actually, if you look at chemistry, and chemistry, I think many people believe that it's a very good case for quantum computers. So, and I believe that too. And I think what's really interesting there is the question about what can you squeeze out of a near-term quantum computer as compared to what can you get out of a long-term, fault-tolerant, all these nice algorithms with all this promise that is down the line. And I think, we can discuss, what we think is down the line, but let's focus on near-term aspect. I think they're actually one of the big differences between, what people thought about some years ago, and maybe it's not, maybe 10 years ago, maybe 7-8 years ago, something like that, when the first sort of hybrid algorithms, those algorithms that try to combine the best of both worlds, the best of what you can get in a noisy quantum processor, and the best of what you can get from a classical computer, including things like the variational quantum eigensolver algorithm class, which is very explored, and I think that there some of the problems that are very tricky there is actually that you somehow need to do a lot of measurements there in order to extract information all the time, feed that back into a classical computer, then update things, go back into the quantum computer, and that in that loop you have to do a lot of operations, and that's really costly. And in particular, it's very costly at this point. Quantum computers are not super fast, and they have noise. You still need to do a lot of things and so on. So reducing the so-called measurement overhead, I think it became known as measurement problem, and I think that's a very precise statement. So a way to reduce that would be really nice. And I think one of the things that makes Kvantify unique is a new way to do exactly that. So we have an algorithm that we called it Fast VQE that has it's not just a fancy name. It sounds fast and stuff. It reduces the amount of measurements that you need to do to make a more precise calculation of a, let's say, small molecule on a quantum computer. So that's basically the idea. So I think, from an algorithm standpoint, that's one of the things we're very proud of, that we've sort of figured out a way to get a quantum computer to using much less measurement overhead to get a quantum computer to give you a near-term quantum computer to give you fairly precise values for small molecules. There's still a scaling problem. All these things, we're not solving everything all at once. That's not what I'm saying. But we managed to figure out how to get, with very few measurements, actually. We were surprised about how efficient this system actually worked. And we managed to get very, very good results on predicting what is the wave function of a small molecule on a near-term device. And we tested it on different platforms, including superconducting circuit, an ion trap kind of platform, and even in the presence of noise, this algorithm actually performs. So that's kind of a way in which I think that we are we are a unique company in that aspect.
Given such algorithm and given your experience, you mentioned small molecules. Obviously, pharma or other chemical clients want larger molecules. How soon do you think quantum computers will be truly useful?
Yeah, that's a really good question, and this is the question that everyone asks, right? I would say if I look at the roadmaps, right, and in terms of how where we're going in terms of the roadmaps, you can see, 50 to 100 qubits with fairly large gate depth in a couple of years, like 2026, or you go to some other roadmap, 2029, and so on. These kinds of things. I think that it depends a little bit. So if you want to run something useful for chemistry in terms of our experience, then I would say you probably need just the algorithm that I was just mentioning. I still fear that, let's say that you had 40 good qubits, and I'm going to come back to what I mean by good qubits, but let's say you had 40 good qubits so that I could sort of implement enough, chemistry information worth of 40 qubits, something like that. I think I would still need on the order of, say, probably between several tens of thousands to 100,000 expensive gates. And by expensive gates, I mean 2-qubit, like a CNOT gate, like, those kinds of gates. So it's still something like 10 to the 4 or 10 to the 5 kind of things, right? And so you're sort of stretching it in that sense. Whether that is possible now, when I gave you that number, that's a number where I'm not even sort of thinking about noise at this point, right? So there I would say, okay, that answer requires error correction, and so now it's a different roadmap, right? So that's the story. What I cannot answer, and where I think the most sort of interesting stuff is going on right now. I'm not one of the people who is completely convinced that we should leave the hybrid and variational algorithms at this point. And this is a very big sort of, it's sort of a discussion in the field, right? Should you leave this because it's never going to work, or move on and so on? And I think I'm not completely convinced of that. I understand both sides of that coin, I think, and I'm not completely convinced yet. I'm probably also inclined to say that it's, even if you sort of say it's not until I have a fault-tolerant quantum computer that these algorithms will actually give me something good, I would say that you need to still prep the quantum computer, and it's a really good, building a good first guess for a wave function that could describe a bigger molecule. Building that first guess, that kind of thing, I think we can do in the sort of near-term era of noisy quantum computers. So I think that's actually where the work is most interesting right now. Now, I'm going to give you something where I'm going to go out on a limb and say that I'm also not convinced that we have seen the last bits of how you most efficiently put information into the quantum computer in the first place. And I think this is actually where there's a loophole in a lot of arguments, in the sense that if you were more efficient about using the qubits that you have, and maybe, you can, if you can live with half of the qubits or a fourth of the qubits or something like that, compress more information, that usually costs you more gates. That's a trade-off. Everyone would say, okay, but what about trade-off and so on? I agree with that, but I think there's still some loopholes over there that should be explored, and where you could maybe think about, can I build very efficient circuits to represent that wave function in a more compact way? And I think that's where a lot of work is being done right now. Also, because this is, when we talk about variational algorithms, it's also very connected to the whole sort of, these variational algorithms have been used in sort of a quantum machine learning context by many people. This is a big area, right? And it's sort of similar questions that come up there.
Given that the algorithms are not good enough yet to deliver true value, what kind of customers are you working with today, and what are they seeking to do?
Yeah, this is really good. And that's also, so some of them some of the customers are very sort of technology interested companies, and I think that's where that's a fairly easy answer there, because technology interested companies are typically just interested in the technology, right? So they're not even sort of focused. So if you have a long-term vision for integrating technology, then some big companies will have an innovation division, and there will be people there who want to just know what's going on, right? Right now, there are probably many of them are overrun by AI and all this kind of stuff, because that sort of, came as a flood in the last year and a half or so, right? Um, but they will be interested in just knowing, what is the prospect of doing this. So some of our engagements with customers are about that. So basically saying, look, where is this going? What would be a near term? And I would then give them basically the same kind of answers that we just discussed, right? What is the near term potentials, and what is the long term sort of benefits and potentials like that. But actually, it depends a little bit. I think that also some of the customers are very interested in actually building building the knowledge and the tool chain that you would need to port a problem onto a quantum computer the minute that it's strong enough to deliver. So that's a different kind of story, right? Because then you need to build a software pipeline that actually has, the ability to take whatever the problem is, put it into the right context, and build the modules that make sure that it can interface with the quantum hardware, right? So those kinds of things are also going on. There we have different clients where some clients are very interested in run something on a quantum computer, run something meaningful on a quantum computer, not asking for advantage, because we don't promise any advantage at this point, of course, but dipping their toes in that particular pond, right? So that's one thing to do. Another thing is to sort of say, okay, let's try to let's not worry too much about hardware. Let's just simulate as far as we can go, and see if an algorithm has promise, right? So like a scaling analysis or quality of solution. This could typically be something in an optimization case, for instance. So that would be a particular point there.
And I'm glad you brought up optimization, because we've been speaking primarily about chemical simulation and fast VQE. Could you talk a little bit about special kind of problems or unique solutions that you might have in the optimization space?
Yeah. So I think that it's very, very difficult, and I'm an optimist here, so that's what I'm going to say before I then say a bunch of negative stuff. No, that's just it's very. I'm unconvinced of the fact that, for instance, what is the benefit of particular types of hardware for one type of optimization, for instance, in annealing or things like that. I would say it's not clear to me where the benefit is. I'm not saying that the benefit is not there. I just, people should, I would be heavily convinced of that. I just haven't seen, where's the sort of benefit. I would go back again to something in the variational algorithm space, where I know that people have tried different kinds of things. So it's kind of similar to the small molecules, actually. So that if you take a similar approach, try variational algorithms for optimization. Now there's a large class called QAOA algorithms, with similar in spirit, in some sense, to the variational quantum eigensolver algorithms. But this QAOA part, I also think that people are sort of becoming more pessimistic. There was a level of optimism that grew a few years ago, and I think it's sort of becoming more pessimistic. And that's basically, it's combinatorial optimization problems typically that I'm aware of, and that this is what I'm talking about. So just want to scope that in, and I think there people are sort of less enthusiastic. I'm slightly more optimistic about that, actually. That you it might just be because you're not treating the search space. I think the quantum computer has an issue sometimes keeping the search space in the right place, and that sounds weird. So let me try to expand a little bit on that. So the fact is that in principle, right, like everyone says, a quantum computer is something that can calculate all possibilities at once, and in principle, we can go along with that kind of thinking, but at the end of the day, you got to measure something. So, and that's one answer, right? So there's no free lunch here, right? And so I would say, I think that what the problem is sometimes, even if you utilize the fact that it can sort of go through different paths, if you can encode a problem into Hilbert space, you can go through different paths, try to sort of figure out that more efficiently. But Hilbert space is a large place, and sometimes your problem is that you get all these exponential possibilities, and then you try to measure one, and if your algorithm is not good enough at restricting you to a bunch of, let's say, viable solutions, then you have a problem. And I think that's where work is being done, and I see impressive work all the time there, where sort of trying to figure out how do you restrict yourself in that huge exponentially big Hilbert space, in those cases where the viable solutions in an optimization problem could be a much smaller space, right? So how do you make sure that in every operation that I do to try to improve my solution, how do I make sure that I don't just go off into this exponential space and just disappear, and all my probabilities are scattered out, and everything, and nothing will work, right? So I think that's one of the key places where I see that there's potential. Figure out how to do that, and naive analysis would say that it's very difficult, but that's what we strive to do, right? Is break difficult problems.
You worked with superconducting and with ions and briefly with cold atoms, and you mentioned annealers. So if you are a betting man or an investor, where would you put your money? On which technology would you put your money to deliver business value first?
Yeah. That's the really good question, right? I'm kind of inclined. So here's the sort of the diplomatic answer is that it's going to be a hybrid technology, which is kind of that's kind of cheating. But I actually think that some of the in some sense I just don't think you can't answer that question right now, because if I look at some of the people have tried to do all this beautiful blog posts out there that are trying to sort of say pros and cons of these technologies. They all have these challenges that are hard engineering challenges in order to make the hardware work. And what I think is good about most of those platforms, and this is where I want to say something positive about it, in terms of whether you could be pessimistic or not. I think it's. I'm not convinced of the people who argue that there's like fundamental physics reasons why one platform would not work. Right? You take a particular platform and then try to scope out that you're like 3 Nobel Prizes away from this working. And that would be a physicist way to say something is difficult. And I'm not convinced of that in the technologies that you mentioned, that we are 3 Nobel Prizes away from those, right? But I do think that the engineering challenge is big in all of those platforms. Now just to say something about where I see, if I look at current roadmaps, right? Who would I say? I'm probably slightly inclined to talk about ion traps and superconducting quantum computers then, because those are just the 2 platforms that I worked with most recently, so it's not a selection as such. But in terms of that, I think that I would pick an ion trap for quality. So if I had a compact algorithm that needed a lot of gates, I would pick an ion trap. If I had an algorithm that required fewer gates but more qubits, I pick a superconducting circuit, right? So that would be my. So actually, it's a practical problem sometimes, right? Which one what is it that you're trying to do, right? So I would say that there's an answer there.
Speaking of Nobel Prizes, and as we get closer to the end of our conversation, I'm curious, if you could have dinner with one of the quantum greats, dead or alive, who would that be?
That's a really good question. I actually yeah. So coming from Denmark, probably people pick Niels Bohr, right? That's kind of the way you would do it. Actually, I would say that a lot of the stuff that we sort of do is based on Feynman's kind of ideas. So Feynman would be really, an interesting character to meet for several reasons, I guess. From that point of view, in terms of how do we scope things out? And I think there's a lot of mathematicians that are overlooked in this field, actually, that sort of came with all the ideas about how. We talked about how, or I talked about how can you figure out what is a good way to encode information? All this kind of stuff is very mathematical, and nowadays people are using all kinds of like fancy group theory and all this kind of stuff. And I love mathematics, so that kind of stuff. So some of the greats in that, including von Neumann or Wigner, physicist, mathematician, while all these people going all the way back to Emmy Noether, who of course introduced the foundations of symmetries that a lot of things in physics are built on. So I think that's also very cool that this is now coming. Things are sort of coming together in these frameworks. So that would also be very cool to do.
And my last question. ChatGPT was sort of a seminal moment in AI. When you think about the quantum progression, do you think it's just going to be gradual, or do you expect a quantum GPT moment where people suddenly wake up and say, OMG, this is real?
I'm gonna go with a technical answer, and then like a real like how is it gonna be perceived in the world? So the technical answer first would be that I think it's going to be gradual, and I think that GPT, when I talk to, we have a bunch of computer scientists and ML specialists in Kvantify, right? And when I talk to them, they're slightly more skeptical about the sort of the GPT moment, like it was like a cliff, and then everything, because in fact, how that developed, if you use the right metrics for those kinds of things, it's actually slow process, but at some point, it becomes a product, and then all of a sudden, right, it gets released and all this kind of stuff. Now, in terms of it, so let's say for quantum, I think the same thing is happening. It's a slow process, and we're slowly just seeing the technology mature, and people solve engineering challenges every day, and you push it forward and so on. I still think that we're the minute that you sort of say, okay, this algorithm, we could take a chemistry problem, for instance, right? Here we have an algorithm on a quantum computer that runs fairly smoothly, probably for, it's not going to run very fast, but it'll run for some time, right? And doing something that a classical computer has a very hard time doing. I think that will be the moment in terms of that use case, right? But to be honest, I'm kind of inclined to say that as society is right now, maybe it's the code-breaking algorithm that will be that moment, actually. I'm kind of inclined to say that that's a pretty good benchmark for what could be there, right? Would be that you say, now I have a quantum computer that's strong enough to break RSA, I don't know, 2048, something like that. Right. And that would be some moment. I think that might be true. I'm not a fan of the scare argument for quantum computing, because I think that, the factorization algorithm builds on other algorithms that will be useful for other things. And I'm also slightly stronger believer that post-quantum crypto will catch up. and that we might see that as that it doesn't really matter too much whether you break it, except for old systems, right? But all of this is all guesswork, and I will be wrong about all of it probably.
Excellent. Nikolaj, thank you so much for joining me today.
Thank you very much.